It's a great pleasure to invite Elena Kosygina to give this seminar. So Elena is from Baruch College in the city of New York, and she'll be talking about some things to do with self-interacting random walks. Thanks, Elena.
Thank you for the invitation. It's a great pleasure to give a talk. And I will talk about convergence and non-convergence of some self-interacting random walks to Brownian motion perturbed at extrema. Right, so I have to start by, well, first, the talk is based on a joint paper with Tom Mountford and Jonathon Peterson. Here are my co-authors. And this kind of self-interacting random walks, we will be all the time on Z, on integers. And this kind of self-interacting random walks, these models go back to Balint Toth in 1995, late 90s. And he wrote a series of papers for all kind of studying different kinds of interaction. So I'm just stating a range of models we are going to consider. So suppose we have random walk on Z, and it is non-Markovian walk, which starts, say, at the origin, and given all the history, the nearest neighbor walk can jump to the right or to the left, just to the neighbor. And the probability to jump to the right is given by a function of a number of crossings of the right edge. So if you have a random walk, right, you here at X, and the probability to jump to X plus 1 rather than X minus 1, you count how many times you crossed that edge in both directions, apply your weight function, and then divide by the sum of the weight functions across this edge and this edge. Function W apparently plays a very important role, but it's a nearest neighbor random walk, which is weighted by the number of times the edges were crossed, nearest edges were crossed. Is there any questions about sort of the model? And the weight function is assumed to be monotone, can be increasing or decreasing. For example, if W is an increasing function, then you are more likely to choose the neighbor which is connected by the edge which was crossed more times rather than fewer times, say. So in that sense, we can say that the random walk is self-attractive. So it's more likely to cross the most visited edge. If the function is decreasing, we say it's a self-repelling, because it's less likely to cross the edges which were crossed already many times. And the type of weight function we are going to consider, here it's written the reciprocal of this weight function is a power function. So roughly speaking, W of n is going to be, we consider two cases. It's like a constant. Well, in particular, this includes simple symmetric random walk. Of course, we are not interested in that so much. Or W of n decays as a power alpha. So that's what's written here. This is a type of models Balint Toth considered, and we will be so recurrence regime corresponds to alpha greater or equals than -1. Right? So this alpha, this parameter alpha, greater or equals than -1. Right. And the recurrence result is due to Davis going back. Actually, there is much more general result. So recurrence follows from this older result of Davis. And we will be concerned with basically two cases: when alpha is 0, and we'll slightly modify the model, and alpha positive. Alpha is 0 was called by Balint Toth asymptotically free case. and alpha larger than 0, polynomially self-repelling. So self-repelling feature I already explained that W is decreasing. Right. And the other cases, for recurrent cases, reinforced case, when W is a positive power up to power 1. These cases were also included in Balint Toth's papers, and then Robin Pimentel for linear case proved the fact that this random walk without any scaling converges to a limiting distribution. The endpoint of this random walk in this linear reinforced case in one dimension converges to a limiting distribution. Again, we will concentrate on these two cases. What's known? So what was done? So the whole point sort of Balint's series of work, one of the points is to show so-called generalized Ray-Knight theorems. Like we know Ray-Knight theorems for standard Brownian motion. These are theorems which say that local times of Brownian motion at certain stopping times behave like squared Bessel processes of appropriate dimensions. So Toth proved, and I will explain what generalized Brownian Ray-Knight theorems are, proved generalized Ray-Knight theorems for these local times of these random walks. And the idea was, how do you use information about local times to extract information about limiting behavior of the walk? So in each of the models, he was stated and proved local time theorems, so approximations for diffusion approximations for local times of edges. And then he was able to show that almost, but not quite, that if you look at the random walk at independent geometric time, so you sample your random walk at geometric times with geometric times independent of your original walk with large mean. So A is a parameter which goes to infinity, S is a fixed number, right? So with this mean, then the random variables converge as A goes to infinity to a distribution which he was able to recognize as a distribution of a constant multiple of Brownian motion perturbed at extrema. Again, I will introduce the processing. He was not able to show that just one-dimensional distributions converge only along geometric sequence of times, but the whole idea was, how do you convert the knowledge of limit theorems for local times into the limit theorems for the endpoint or functional limit theorem of the walk. And if you, on a trivial level, completely trivial level, if you have a discrete random walk, just the discrete process on a graph, just you have any graph, and if I tell you how many times each vertex or each edge was crossed at every time, so all the local time, all the local times, all the numbers crossings, the whole landscape all the time, you can reconstruct the path. And if I give you a path, of course, you can reconstruct the landscape of local times. So Ray-Knight theorems don't give you the full landscape. Ray-Knight theorems just give you the distributions at certain heating times, right? So they give you much less information in general. And the question is how much, one can think about the question, how much Ray-Knight theorems determine or define the original process. It's too vague a question or too general a question to ask, but basically this talk and the work of Toth previously somehow tried to see which information can be extracted from Ray-Knight theorems. Right. So in this paper, in this talk, I will say that the main finding is, which was very unexpected to us, is that in some cases we can prove theorem, the functional CLT, but we have an example of a process, essentially, whose Ray-Knight theorems and are the same as for Brownian motion perturbed at extrema, but the process does not converge to predicted Brownian motion perturbed at extrema. So this is a short kind of overview of what's to come. Again, are there any questions? So I was talking about Brownian motion perturbed at extrema. Here is what the process, what is the candidate limiting process for this kind of walks. So we fixed two parameters, theta plus and theta minus, right? And Brownian motion perturbed at extrema with these parameters is defined as a unique pathwise solution to this this equation. So this is Brownian motion perturbed at extrema. It's a standard Brownian motion plus sup times theta plus one parameter and inf plus inf another parameter. And the process, say, starts from 0. So if you try to imagine this process, so away from its extrema, so on its range, it behaves completely like Brownian motion, standard Brownian motion. When it is visiting its sup at the extreme point, depending on the sign of theta plus, it's either pushed forward away from its range, or if theta is negative, it is pushed inside the range. The same is a similar thing happens at infimo. The process was introduced by Le Gall in 1986, and it came up in various contexts and was studied by itself by many people: Burgess Davis, Perman Werner, Carmone Petit-Dior, Chamon and Doni, Yuan Hu. So many people studied. So this process is well defined. And the important part about this process that it has Brownian scaling, which is quite easy to see if you put constant here and C over constant there, right? Just constant S over C squared C, right? Brownian motion. So you see that this process, due to the fact that Brownian motion has this scaling, so this is in distribution, is a standard Brownian motion as well, right? You see that you get the same process. At least it is intuitive that this process has a Brownian scaling, right? So also, I mean, what other properties? Another property I would mention of this process is that even though the process itself is not Markovian, because at each time somehow you need to know its sup and its inf, the triplet inf, the process itself, and sup is a Markov process. So this is a candidate process for the limit, for rescaled limit of random walk. And indeed, for simpler models, previously, Burgess Davis proved a functional limit theorem, which showed basically you can think of it. How do you generate Brownian motion perturbed at extrema? What's one way to do it? One more thing I wanted to say is, you see that the parameters I mentioned, they are from -infinity to 1, not including 1. It's also simple to see that you cannot extend. I mean, there are no solutions for 1 and above. If you, for the moment, forget about infimum altogether, right? Forget about infimum, and if you look at this equation and you bring the theta plus to the other side, theta plus term to the other side, right? You see that if theta plus is equal to 1 or more, then this side would always be negative. This side would always be negative, and Brownian motion distribution, we know that it's normal, so there cannot be a solution to such an equation. So this is a natural range of parameters, theta plus minus, from negative infinity to 1. And if you want to say simulate Brownian motion perturbed at extrema, one can use Davis's result. So you pick two parameters and start random walks from 0. Originally, it starts jumping by 1/2 to the right and left. And it does so as long as it's strictly between its infimum and supremum. When it comes to the maximal point, it jumps to the right with this probability. When it comes to the minimum point, it jumps to the left with this probability. It's like once it's perturbed at its extrema, this walk. And this walk, after diffusive scaling, can be shown, and Davis has shown, converges to Brownian motion perturbed at extrema. One might ask why these probabilities. It's sort of, again, it's easy to see why these particular probabilities. Again, if there is an interest, I'll explain. If not, then I'll go on. Any suggestions? Well, okay, I will go on. So the model we consider is slightly different from Balint Toth's model. It's just in that it is a little bit more general. What is the difference? The difference is that we look in Balint Toth's model, there was a 1 and 2 here, 2 plus epsilon. Then in our case, we consider P between 0 and 1, and kappa is just the positives. It's slight generalization. You can think about as C over N if you wish. And the case P larger than 1 is covered by the fact that you can take C equals 0 and not have this term at all. So since we have two cases, we'll consider both asymptotically free case, alpha equals 0, and then we'll consider the other case, alpha positive. So to formulate a theorem, so we have a positive result in alpha 0 equals 0 case and negative result in alpha positive case. So to formulate the result, we first need to compute two quantities. The sum of reciprocals. So what the sum of reciprocals, what do they have to do with anything? So if you are at the point, if you are, for example, starting at 0 and reaching, say, a positive integer, then you have edge connecting you to x plus 1, and you have edge connecting you to x minus 1. And the first sum actually has to do, the whole thing is deep in the background, is related to Erd models. So the first sum has to do with W of even numbers. So every time you visit X, you look at how many times you crossed this edge, and it's always even number. So this particular quantity has to do, and I explain in a moment, with the crossings of the right edge. And the other one has to do with crossings of the left edge from where you currently are. And the gamma, one can always show that the limit exists. It's easy to see that the limit exists of the difference V1 of n and U1 of n gives you a main parameter, which is the parameter of the limiting Brownian motion perturbed at extrema. It has the same theta plus and theta minus, and they are equal to this gamma. So on So let's see a little bit how this happens. So when you first reach, say, positive x, for example, right? The probability, so you already crossed this edge once, right? So what is the probability to go to the right? Well, the probability to go to the right from this point at this moment is W of 0 divided by this sum. W of 0 plus W of 1. You crossed, here is your 1 and here is your 0. So that's the probability. And then suppose you went to the left, right? Next time you return, the probability to go to the right is given by that, and so on, right? Suppose you went to the right, and I wrote just the first few. And these left and right jumps, or arrows, if you want, can be constructed throughout the whole model. And then you can have your walk just walking deterministically on already constructed sequence. So Rubin's construction, we take at that point, we look at independent exponential random variables with parameters W of 2i. We call them red balls for EARN, and exponential with parameter W of 2i plus 1. So I can be 0, 1, 2, and so on, right? And what is the mean? Then in this setting, what is the meaning of this U and V? So the meaning of 1 over W is the expectation of this random variable. So this is the waiting time for the nth jump to the right. And this is the expected waiting time for the nth jump to the left, right? And then if you take the difference of the two, so we are in the case alpha equals 0, if you take the difference of the two, how long it takes to jump n times to the left minus how long it takes to jump n times to the right, well, it's easy to show that the difference converges under our assumptions. It converges to negative gamma if 1 over W is decreasing, and to positive gamma if 1 over W is increasing. So the meaning of this gamma is the expected time discrepancy. You think about one ball added or removed from EARN in 1 unit of time. So expected time discrepancy, and it gives you this this parameter. How many more red balls or how many more blue balls, how many more red balls you get in comparison to blue balls. So if you want to construct the arrows here, you see the competing exponential random variable. So you just look at the blue arrivals and red arrivals, and the jumps to the left and to the right will be done according to which arrival comes next, blue or red. And this can be constructed independently, IID, throughout the whole Z. And then your walk knows at each point what to do. So, and this description makes this definition of the parameter very, very natural. So somehow this gamma measures the discrepancy, and which discrepancy then becomes the drift, sort of the push parameter in Brownian motion perturbed at extrema. So let me remind you the model that we consider, and the theorem we were able to prove states that in this case, in asymptotically free case, for any p larger than half, we have indeed convergence to Brownian motion perturbed at extrema with parameters gamma and gamma. It's a functional limit theorem. So we wanted to prove it, we expected to prove it, and I will say a few words about the proof. It did not come as a surprise. But what came as a surprise is that we really thought that polynomially self-repelling case, even though technical details are different, we will arrive to the predicted process just as well, but it happened to be not the case, and that came as a surprise, and it was really interesting. So how how is it done? Well, the method is on a large scale. The method is standard. It's a martingale technique. So Brownian motion perturbed at extrema is Brownian motion and this perturbation. So it is natural, and it was done for many other self-interacting random walks, like for excited random walks. Natural to subtract, to look at the increments of the process and make it construct a martingale by subtracting the expected drifts at each step. Like it's like Dub's decomposition, essentially. So you get a martingale plus the drifts. And then if you can show that this martingale has quadratic variation, linear quadratic variation, linear growing quadratic variation, you have a good chance to show that this is this converges to Brownian motion. And then again, I'm describing it at a level where without any technical details. Then Ray-Knight theorems come very handy in proving the fact that these drifts will correspond to maximum and minimum. So this converges. So the difference between this and rescaled converges. Okay, the difference becomes small. So the probability that the difference is larger than epsilon square root of n is small. And then you put two things together. That's another thing. And one can show that the convergence to Brownian motion perturbed at extrema takes place. So this was not really new. The technical details are new, but the idea of using martingales goes back. I don't know when exactly it started. Martingale center limit theorem is known for a long time. Right. And then we decided to really to prove polynomial self-repelling case. From Ray-Knight theorems and from work of Balint Toth, the candidate process was a multiple where alpha is just appears in asymptotics of our W function. So it is n to the alpha, right? So alpha is this parameter. And no matter what alpha is, except for the scaling parameters, the parameters for perturbation were predicted to be 1/2, 1/2. I don't have I wish I could get these parameters in a very intuitive way. But even Balint Toth wrote in his paper that he cannot give an intuitive explanation. We also tried to, these parameters come about from Ray-Knight theorems. And so the result we proved, since it's a negative result, we took a particular representative, 1 over n to the alpha, n plus 1 to the negative alpha, that's our weight. And we considered a self-interacting random walk with this weight function. And we've shown that in spite of the fact that along independent geometric times, one-dimensional distributions converge to one-dimensional distributions of this process. In spite of the fact that generalized Ray-Knight theorem, so edge local times, converge to local times, half of the local times of Brownian motion, of this Brownian motion perturbed at extrema, the process itself does not converge to the candidate process. And one can make a simple argument that then it doesn't converge to any Brownian motion perturbed at extrema. So if there is a limit, which we do not know, then the limit should be some different process, if it exists at all. So just since I mentioned so many times generalized Ray-Knight theorems, let me give just some background of what on Ray-Knight theorem, on generalized Ray-Knight theorems. So first, let's start with the Brownian motion and define. So in case of the Brownian motion, the just standard Ray-Knight theorems says that if you look at the local times at the first heating time of a certain level, or at the first time the local time at 0 exceeds given number, the resulting processes are of local times are squared Bessel processes of appropriate dimensions. So to remind you, squared Bessel process is a solution of this SDE, where delta is a dimension, can be positive or negative. In our case, we are interested in non-negative dimensions, right? For example, if dimension is 1, right, we have a square of the standard Brownian motion. I mean, 2, it's a distance from the origin of two-dimensional Brownian motion, and so on. So the important part about, just one part about squared Bessel processes, that if delta is greater or equals than 2, then if you start the process from 0, the probability of returning to 0 or never returning to 0 is 1. And for delta less than 2, the first heating time of 0, wherever you start, is finite with probability 1. And maybe one more thing to mention is that for delta equals 0, for dimension 0, and x positive, this process up to a constant arises as a scaling limit of a critical Galton-Watson branching process with offspring distribution nu. So nu over 2 here, nu over 4 here arises, this is nu is a variance of the offspring distribution, right? And so this connection with branching processes at the level of Brownian motion is a very well studied, very well known. And it is these processes, squared Bessel processes, arise as a Ray-Knight theorem for Brownian motion perturbed extrema. So let me, I mean, if you prefer to, you can even think zeta plus zeta minus is equal to 0. You have just your Brownian motion perturbed extrema is just unperturbed Brownian motion, and you should get standard Ray-Knight theorem. So denote by LA sub t the local time of this process at A up to time t, and define for positive h, tau A is a hit, sort of the stopping time, the first time the local time exceeds at A exceeds h, right? For example, if I'm here at A, the first time the local time exceeds h at here. And Ray-Knight theorems state that you look forward and backward from here. You look at the, so your local time here is h, and then you are looking at the local time forward from here. So this is for your local time process is so indexed by S. So for S is positive, this is you're going this way. For S negative, you're going that way. I mean, I put plus or minus S. So given H, the processes looking forward and backward, processes of local time, are independent squared Bessel processes. And for case Brownian motion perturbed extrema, the dimension is given by 2 times 1 minus zeta minus. So this is the red part. And as soon as you reach the origin, I started here with a negative A, it becomes, the dimension changes, you remove the dimension changes because now we are in the positive part where the process is pushing to the right, Bessel squared process of dimension 2 zeta plus. And looking the other way, the local times are Bessel squared process of dimension 2 zeta minus. So in any case, without many details, at the time when the local time exceeds, first time when local time exceeds h, the local time processes going for here or here, forward or backward, are squared Bessel processes of appropriate dimension. Balint Toth proved that for the random walks, for his self-interacting random walks, if you look at rescaled edge local times, then they converge to a half of this. They converge to these processes, half of local time processes for Brownian motion perturbed at extrema. So that was one of the facts that we proved. Is there any questions, any comments, maybe? So, yes?
Just any comments from the audience?
Yeah, there is one here.
I was just wondering, it's more about the picture. Can the local time be 0 somewhere inside the interval, or in the red portion?
Yes, local. Again, it depends on the parameters. For example, here, right? Here we have parameter 2 times 1 minus theta minus, right? So when theta minus is positive, local time can be 0.
Ah, yeah? Okay. Okay, so it's different from standard Brownian motion. Okay. Okay, thanks.
Right. Well, it is. Well, if theta, see, for standard Brownian motion, theta minus is 0, so we have 2, and then it does not hit 0.
Thank you. Yes, it was my question.
Thank you.
Yeah, please go on.
So, well, I've written, I think that the picture is, in that sense, more useful. I've written the theorem, how it's stated in Carmona, Petit, and Yor. Again, given 2 parameters. Why did I say 0? It should be 1. Right. For a less or equal than 1 and h greater or equal than 0, we have the fact that these 2 processes going forward and backward are independent. And going backward process is absorbed at 0. It's always absorbed. Remember, theta minus can be negative. So as soon as it hits 0, it is absorbed at 0. And going forward, it's a gluing of 2 processes, 2 Bessel squared processes of stated dimension. Now, again, what are the generalized Ray-Knight theorems for polynomially self-repelling, self-interacting random walk? So polynomial self-repelling means that W of n decays as 1 over n to the alpha. So we look at, but it's very similar, meaning that at time fix A, and at this time we look at the time of the n times h up crossing. So we are scaling things, right? So we look up to the time when there is a up crossing n times h up crossing from this point, right? And we rescale. We rescale, and then we look at this time. We look first at down crossings from this level to this level, from this level to this level, and so on and so forth. And after rescaling by n, this process converges to a multiple of squared Bessel process of dimension 1. That's for polynomially self-repelling case, right? No matter which alpha is, alpha appears only in the scaling, and the rescaled edge local times, how many times you crossed each edge, starting from the time when you up crossed this many times, converges to squared Bessel, multiple of squared Bessel process of dimension 1. And going forward, you look at up crossings from this edge to the next, and so on and so forth. This is a process, how many times you up-cross this and this and this and that, and you rescale, and it converges to a gluing of two squared Bessel. Well, in this case, the gluing happens to be the same Bessel squared process of dimension 1. So this is Bessel squared process of dimension 1. I mean, so this is generalized Ray-Knight theorem saying that these local times converge to multiples of Bessel squared process of dimension 1. And when one compares these two Ray-Knight theorem, one realizes that yes, theta plus equals 1/2 and theta minus equals 1/2 give you the idea that local time edge local times converge to those processes which are obtained from Brownian motion perturbed at extrema with parameters theta plus equals 1/2 and theta minus equals 1/2. So in that sense, Balint Toth proved that's what he calls generalized Ray-Knight theorems for self-interacting random walks. Right. Now, why? So I'll try to explain next. So again, are there any questions?
Yeah, I think not. So,
Okay. So what goes wrong with a polynomially self-repelling case in comparison to Brownian motion perturbed at extrema? So if we look at Brownian motion perturbed at extrema, the candidate process, and we look at the local time, right? At the first time when the local time at 0 exceeds h, and I put a half here because edge local times are related naturally to a half local time at the at the point. So that's why you see 1/2 here. So if we look at this local time process, and then we look at the difference of the process of difference of local times, you wait until the local time at the origin exceeds h plus 1. And you look at the difference, the process of differences of local times here. Then essentially, when h is large, very large, this increment of local time is independent from this process, from the original one. So the increment is independent. Not quite, but it's essentially independent. Right. And then for polynomial self-repelling walk, when we look at the same situation, so we look at time at the first time when the number of up crossings exceeds hn, right? And then we look at this process of edge local times, rescale it, and then we look at additional edge local times, and we look at these two processes. What we found out in our basically calculation, that these two are correlated, and this scaling parameter, this has to do with variance. It is not the right one. What happens that this v depends on h, how far. So the additional local time starting from h, the additional local time depends on h, and it converges to 1 as h goes to infinity. So what happens is that this additional time, given the past age local times, the additional time behaves differently. So even though the process, if you look at it at h plus 1, it scales and it behaves as the one for Brownian motion perturbed at extrema, the addition, sort of due to these correlations, the addition is not happening in the same, say, independent way as for Brownian motion perturbed at extrema. So again, once you found this out, you say, okay, we have a result about local times. And there is a lot of work going to how do you translate result about this, the fact that local times add improperly in this process to the result that the whole process does not converge to Brownian motion perturbed at extrema. So this was sort of another part of like technical part to handle, but the main finding was that Bessel squared processes for Brownian motion perturbed at extrema local time processes have very nice additive properties. And we discovered that for rescaled random walks, H-time local time processes, even though the process, the sum of the processes already behaves in the same way as for Brownian motion perturbed at extrema, the additive property is violated. Right. And then we were able to translate it into the result of non-convergence.
But why do you get convergence at these geometric times? Why?
That is a good, well, first, geometric times are completely independent on the, so basically it says that if you sample at geometric times, right, so you perform a certain, so it's I mean, because at geometric times you do not have, they don't give you, they don't somehow show you what is happening. I don't know how to answer the question, why do they converge? So this was a finding that occurred to Balint Toth. He basically wrote down the local limit theorems, local limit theorems along geometric time. So when you write local theorem, you write the probability that, you write that the probability of random walk at time n t is equal to square root of n or some k, right? But when your time is a random variable, right? You have and it's exponential. It's a geometric random variable. You actually have certain averaging, sort of. You have a sum. You say depending on what this random variable is. So you have this ti, or I don't know how. Right, and then you multiply that the probability of ti, probability that ti is equal this and that. So there is certain time averaging occurs in the when you consider geometric times, when you consider when you consider geometric times, and I think due to that, this non-convergence was not sensed in any way. He actually made a conjecture that there should be convergence to Brownian motion perturbed at extrema.
But you don't see that on your construction.
Our construction does not involve any geometric times. Right?
Yes, but taking geometric times, then you get convergence. You don't see that in
well, we did not try. I mean, we did not. So in our construction, what we tried to show, we tried to show convergence. We tried to show functional limit theorem. Right. So, and we applied our sort of method. You decompose and you get a martingale, you still get a martingale, and you get an additional thing. But what we discovered that martingale, inside that martingale, there are strong correlations, and it's not sort of the quadratic variation process does not behave properly.
Maybe it's a related question. So it is known that you have this convergence of one-dimensional marginals, provided that you take a random time.
Yes.
But it has not been proved that you have convergence of one-dimensional marginals if you take a deterministic time.
Correct.
do you think that this might also be true, or does your result indicate that this might be false? Or
so our result, unfortunately, says that there is no functional limit theorem, but
Yes.
our result does not say that there is no one-dimensional convergence. So we think that actually one-dimensional convergence might be true, and somehow it's a work in progress to try to figure out. So imagine how can exist sort of a process that would be quite interesting, which has the same one-dimensional distributions as this Brownian motion perturbed at extrema, right? Exactly the same one-dimensional distributions and exactly the same Ray-Knight theorems. The limiting process has exactly the same Ray-Knight, if it exists, has the same Ray-Knight theorems as this process, right? And the same, then if one-dimensional distributions converge, would have the same one-dimensional distributions. And it would be still not Brownian motion perturbed at extrema. So one doesn't really know what to think. We think that the process can be constructed, but we don't know whether the answer to the question, whether one-dimensional distributions converge to those or Brownian motion perturbed at extrema. Right. Of course, I mean, there are plenty of processes which are Gaussian with the right mean and variance, like a straight line, z times t, right? Standard norm times t has the same one-dimensional distributions as Brownian motion. There are plenty of processes, and it's not a Brownian motion. Oh, so z square root of t, right? But when you look at local times, you don't have by far not the same picture. Here we have a picture of local times exactly correct, right? Then, so I do not know what really I would think there should be convergence, but I'm not positive. We don't have the result. Yeah.
So
Thank you.
Yeah.
So when alpha is equal to 0, something reduces here.
Oh, when alpha equals 0, okay, so alpha is equals 0, you basically perturb from 1, right? When alpha is 0, you have 1 plus a small perturbation, right? So as opposed to starting from 1 to the n to the alpha. So somehow these terms that we consider the variance, so the sort of what happens variance wise is different from alpha equals 0. So this is a more kind of it happens to behave differently, yes. And you can also notice that if you try to take alpha equals 0 here, take a limit, there is no sort of continuity. This goes away, but these parameters do not depend on alpha. So currently, basically, we decided that we will try to see if we can construct a process. How one can try to construct a process from a walk. One can do some coarse graining, right? To look at the process when it moved a little bit by epsilon square root of n to the right, epsilon square root of n to the left. We were successful doing that for excited random walk. In Markovian case, in Markovian cookie stacks, when for a long time, Jonathon Peterson and I had no idea whether there is convergent because none of our methods worked. And then Tom joined us and we tried this coarse graining, and coarse graining technique worked. With polynomially self-repelling case, we don't expect that the coarse graining technique will work to show there is no convergence to that, but maybe we can show the existence of the process. And I don't know how successful we will be. Yeah. Thank you for your attention and question.
Okay, so why don't we thank Elena for a very nice talk. And could I open the floor for questions? Any more questions?
Well, if I go back to the constructive result, so I didn't get
Positive result.
Yeah, the positive result. I didn't get why you expected the convergence to the process. So could you go back to that? And you said it wasn't expected, the convergence was expected. I didn't get why.
When we started this project, we already knew from Balint's work that local time processes are converging, rescaled local time processes are converging to those of this Brownian motion perturbed at extrema. This was already established. And along geometric times, this independent geometric times, it also converges to the one-dimensional distribution of this process. So the candidate somehow was identified for us.
Yes, that I understand. But forgetting Balint's result, could you give a reason why you expect convergence to that process?
Well, basically, the perturbation part is kind of clear. So the perturbation part intuitively is not intuitively is not difficult. It follows from Ray-Knight theorems. So perturbation part, I mean that the fact that at supremum and at infimum, it receives a push, right? Imagine you come to the supremum, your random walk comes to the supremum, that how much push you receive, right? So each time you come to supremum, you have here 0 times you crossed, and here you crossed a few times, right? And then you can basically, so and then you need to have, roughly speaking, not quite geometric number of attempts, depending on your function, of course. Each time you make an attempt to go from supremum up, you are either successful or not. Next time you come, you added 2 things, two visits, and then you try again to come up. And eventually you succeed. So this way you can actually try to compute the drift, how much drift you accumulated while trying to go from here 1 step up. And this drift expressed in this function and this difference which I explained gives you the excess, sort of excess drift, right? And this tells you what is going to be the parameter gamma. What is much harder to me to explain is what happens inside, right? But inside, right, what happens in between minimum and maximum? The fact that a gamma parameter arises, it is from these Earn models and looking at what drift is actually, okay, what I said is not quite correct. You accumulate drift at each extreme point, right? So going from here to here to here, and then going from here to here. So how much drift you accumulate at an extreme point. What is not obvious, and in this case, was not obvious, is why inside you have Brownian motion, right? So basically, it says that the discrepancy between number of times you go up and number of times you go down, right? So discrepancies behave in the right way. So there is actually a limit theorem for these discrepancies. They behave very regularly, normally, right?
Okay, thanks.
I mean, there is no, there is a calculation which basically says that inside, in spite of this Earn, in spite of these perturbations, that you have this many times and this many times you move to the left. That's what drives your essentially limiting process, the variation of that martingale which I've shown. So that quadratic variation, you can basically look at the discrepancies and they give you that quadratic variation, and you find that it grows linearly. And that's enough to show that inside you have Brownian motion.
Thank you.
So if I understand well the result, it's kind of says that if Wn grow,
we actually have sort of half the Brownian motion, right?
Okay, but this is for p larger than 1/2, right?
Oh, yes, that's a very good point. Yeah.
So do you believe that when p is smaller than 1/2, you might also get into trouble?
Well, so the expectation,
because you have no negative result for p smaller than 1/2, right?
So we do not have any result for p up to 1/2, right?
Okay.
So we do not have the result. We have result only for p larger than 1/2. But we believe that this is because of our methods, because the method I described, just by making dupes sort of decomposition, we believe that it does not work for just the method does not work for p less or equals than 1/2. But if you do coarse graining, again, if you look at sort of the first time you hit epsilon square root of n and minus epsilon square root of n from the current position, right? Then that might actually work for p less than 1/2. So the sort of if you would like a conjecture that this still holds, but requires coarse graining. It requires a different method, maybe something else, but it requires a different method. It's just we cannot handle it with our technique.
Thank you.
So I was just curious. Can you get one of these processes where theta plus and theta minus are different?
Well, yes, of course. Basically, what you need to do, you need to take one W to the right of 0 and another W to the left of 0. Another W meaning the parameter gamma depends on C. The parameter gamma depends on C. So when you look at this series, these sums, right, which define parameter gamma, essentially this C contributes alpha is 0, C contributes and most. So you could just take one something which converges to one gamma to the right, and something different W which can have another gamma parameter to the left, and you will get different parameters. We didn't do it. There is still something to handle at 0, but I believe that will construct just any Brownian motion perturbed extrema. So this could be done gamma plus and gamma minus by choosing different weight functions, which give different parameters.
I see. Thank you. Are there further questions for Elena? If not, why don't we thank her again for a very nice talk? All right, thanks, Elena.
Thank you.
Thank you, Elena.